All right, our next section is on the electron volt. What is an electron volt? Well, the name actually tells you exactly what it is, but we'll go over how we come up with that. So an electron volt is a very small unit of energy when we compare it to joules. It's the energy gained when you take either a proton or an electron and you take it through 1 volt of potential difference. So if we plug it into our potential energy or electric potential energy equation here, you just take charge of an electron times 1 volt, and we find that an electron volt is 1.6 times 10 to the minus 19 joules. So it's real tiny. But that basically means that an electron volt is less of an equation and more of just a definition of how much energy you gain by an electron going through 1 volt of electric field. But let's talk a little bit about electric fields right now. So if an electric field is uniform, like when we talk around a point charge or between 2 plates, we know that voltage, or change in voltage, is going to be equal to electric field times how far it passes through it. And from an earlier section, we know that electric field is just equal to K, Q over R squared. We put these suckers together. What we end up with is that our change in voltage, I'm just plugging an electric field into there. We get that our change in voltage is K, Q over R squared times R. R cancels. And what we're left with is that K, or our voltage, is equal to K, Q over R. Now, the nice thing about voltage, and you guys are really going to like this for when you have to do calculations, is that it is not a vector. It's a scalar, meaning all that matters is the sign. So when you add them up, it doesn't matter direction, meaning you can completely get rid of all that extra stuff we did when we found electric field and electric force in the first 2 sections with finding angles. You just straight add these suckers up. So what does electric potential look like as a function of distance? This is number 12. So let's say we have some charge here. We'll have a positive charge. This will be at a distance r away. And this is like the edge of the particle. What we find is that we get exponential growth as we approach the edge of the particle, and we get exponential decay as we go away from it. So this would be our positive charge. This would be a negative charge. And then over here, this would be our voltage. So voltage becomes 0 as we go towards infinity, and it gets bigger as you get exponentially closer to them. So I'm going to erase this. We'll come right back, and we'll work on a problem with them. All right, so I want you guys to imagine that I have some particle, big Q, right here. I'll just put big Q. It's positive. It's got a charge of 20 microcoulombs. And from infinity, so imagine this is infinity away. I can't actually do that on the board, surprisingly. I've got this little tiny charge, 3 microcoulombs, and I want to bring it from infinity down to a distance away of ½ a meter. I believe it's ½ a meter. Yes, ½ a meter. I want to know what amount of work am I going to need to do that? Well, the first thing I need to think about is how much electric potential energy does it have, or how much voltage does it have when it's infinitely far away? Well, if it's infinitely far away, it means it's basically got no voltage. So voltage at infinity equals 0, meaning that's my starting point. Remember that chart we had on number 12 where it shows dropping off? As we get to infinity, it's basically 0. So now we have to find out what's the voltage going to be when it's at ½ a meter away, and then the difference is just going to be 0 to that. So voltage at 5 meters is going to be K, Q over R. When we plug that in, remember we're just using the voltage of the initial object, because remember voltage doesn't, our big object here, because voltage doesn't care about what your charge is when you get close to this object. It just cares about what the electric field is around this guy. We can look at electric potential energy later when we use that charge, but it really is irrelevant to this problem. Voltage is just caused by the object making the field. So K is 9 times 10 to the 9 Newton meters squared per coulomb squared. This next guy is 20 microcoulombs, so I'll do 20 times 10 to the minus 6 coulombs, and then I will divide that by the radius of ½ a meter. And when I plug that all in, I get a value of 360,000 volts. So that gives me what my voltage is going to be, because if I go from 0 to that, this is just my new voltage. So that is the amount of voltage, but now we can just plug voltage in for electric potential energy, because remember, as I go from here to here, there's work being done that is opposite to my change in electric potential energy. So at infinity, I have electric potential energy because it wants to, or I don't have any because this thing wants to get away from it. But as I get closer, I'm adding. So they should just be opposites of each other. Electric potential energy is equal to work. Electric potential energy we represent by negative, work is just going to be, there we go. Work is just going to be negative Q delta V, because that's what our electric potential energy is equal to. So when we plug in for Q, wonderful. There we go. When we plug in for Q, our voltage of an electron is our charge of an electron is negative 1.6 times 10 to the negative 19th coulombs. Our change in voltage is 360,000. And when we plug those in, that is going to be equal to negative 1.08 joules of energy. And is that by the electric field, or is that on the electric field? So I want you to think about that. Is this work by the electric field? Well, the electric field does not want this coming closer, right? This is a positive charge. All of our electric field lines are pointing away from it. So what we should see is that that this is work being done on the electric field. Work by the electric field is what it naturally wants to do. Work on is when you work against it. This positive doesn't want to get closer, so this is going to be work on the electric field. All right, on number 14, I want you to find the potential difference, or the voltage, at point P, based on the fact that we have a 5 microcoulomb charge here and a negative 2 microcoulomb charge here. So go ahead, attempt it, and we'll be right back to go over it. All right, so first thing I want to do, since this is a scalar, all I need to do is figure out the total distance from it. It doesn't matter the angle or the direction, other than the fact that it's going to be positive from positive charges and negative from negative charges. So for the voltage caused by charge 1, it's pretty simple, just KQ over R. Just plug in my numbers, boom, nice and easy. Now for the voltage of 2, it's going to be a little bit different because I'm now at an angle here. I've got to figure out what this distance is. So just Pythagorean theorem it, 4 squared plus 6 squared, square root of that, and then I squared. I don't need a square there. There we go. Leave the square root like that. I don't know why I put a square on there. There we go, corrected it. And when I plug that in, I get negative 2,500 volts. Up here, I get 11,250. When I add them together, I get a total voltage of 8,750 volts. So now what I want you guys to do for part B is I want you to find the work to bring a charge Q3. Am I still on? Perfect. Charge Q3, which has a charge of positive 4 microcoulombs, from infinity to point P. So go ahead, figure out how much energy or how much work we need to do to bring a charge from infinity to point P that has a value of positive 4 microcoulombs. So when we look at this one, we know that the work we're going to do is equal to the negative change in potential energy. Considering this one is getting closer, a positive, to a net positive voltage, it's going to take energy, so we should hopefully end up with a negative number, which we do. Just equal to the negative value of our charge times our change in voltage. At infinity, our voltage is 0, so it's just going to be the voltage we end up with. So we take negative 4 times 10 to the 6 coulombs. That negative's from there, not from the charge. We multiply it by the voltage at the end, and we end up with 0.035 joules of work done. So this would be by an external force not by the electric field, because we're going against the direction the electric field wants to go. We got one more problem we're going to try out, and we'll be done with notes after that. Okay, for our last section here, we have two parallel plates with different charges on them. We have a positive plate, a negative plate. We have a proton that is initially traveling up towards the negative plate with a velocity already of 3 times 10 to the 6 meters per second. The electric field strength between the two plates is 8 times 10 to the 4th volts per meter. And our mass of our particle, which is a proton, is 1.67 times 10 to the minus 27 kilograms. With that information, I want you to determine what is the delta V going from the positive plate to the negative plate. What is the change in electric potential energy, and is it work done by the electric field or an external force? And finally, what is the velocity of the proton going to end up with? Go ahead, pause the video, try to do as much as you can, and when we come back together, we'll go over it. Okay, so the first part should be fairly simple. We know how much, with the electric field, we know how many volts there are per meter. It's only half a meter, so we just divide that by 2, or multiply by a half. And what we end up with is 4 times 10 to the 4th volts. Since we're going from positive to negative, though, that means we should have a change of negative 4 times 10 to the 4th volts. When we come down here and use that to solve for our delta UE, remember our delta UE is just going to be equal to the negative of the work, which is just negative Q delta V. The charge of a proton and an electron are both 1.6 times 10 to the minus 19 coulombs. Multiply that by the change in voltage, and we end up with 6.4 times 10 to the minus 15 joules. Still a pretty small number. And then finally here at the end, we know that our change in kinetic energy is just going to be equal to the amount of energy we lost in our electric potential. So we set our change in kinetic energy equal to our change in electric potential. So 1/2 m final velocity squared minus initial velocity squared. When we rearrange, we're going to double this side, divide by m, and then subtract VI. Or sorry, we should be adding it. My apologies. There we go. And when we do that, we end up with a final velocity of 4.1 times 10 to